Okay, let's dive right into some incredible engineering detective work. We're going to be looking at one of the most complex flying machines ever built, the helicopter. But deep inside of it, there's this invisible battle raging, a constant fight for the very air it needs to fly through.
So at the very heart of a helicopter, you've got a powerful turboshaft engine. It's an absolute marvel of engineering. But here's the paradox, the really weird part. This engine, the machine's own powerhouse, is in a constant battle with the giant rotor spinning right above it. And you know what they're fighting over? Air.
All right, so let's meet the two main players in this aerodynamic drama. First up, you have that massive main rotor. You know, the thing that gives the helicopter its lift. And second, you have the incredibly powerful turboshaft engine, the heart of the machine, which has to suck in huge amounts of air just to generate thrust.
Now here's where the fundamental conflict comes in. The main rotor's whole job is to create a massive column of downward moving air. We call that downwash. It's literally what keeps the helicopter hanging in the sky. But at the exact same time, the engine needs a steady, clean flow of incoming air for combustion. So you've got one part pushing down and the other sucking in, and they're right next to each other.
To put it simply, for that engine, it's kind of like trying to drink through a tiny straw in the middle of a hurricane that you yourself are creating. This makes predicting the exact airflow into the engine incredibly difficult, but it's also absolutely critical for performance and, safety. And this diagram just illustrates the problem perfectly. As you can see, the engines, which are marked here in zones I, 2, and 3, are placed directly underneath that main rotor disc. Now, this placement is necessary for a dozen different engineering reasons, but man, it puts the engine inlet right in the middle of all that chaotic airflow.
For years, engineers have been trying to model this really complex interaction. But as it turns out, many of the older models, well, they were missing a key piece of the puzzle.
So you have these two competing forces, right? On one side, you've got the main rotor's effect, which is this huge, powerful downwash. And on the other, the engine's effect, which is a powerful, focused suction. For a long, long time, the calculations focused almost entirely on the rotor's impact, mostly because it's so massive and, well, obvious.
But as this research points out, that was a huge oversight. The study says it directly. The previous studies have ignored the effect of powerful engine suction on the airflow. So here's the crucial point. While everyone was watching the hurricane coming from the rotor, they weren't fully accounting for the powerful vacuum cleaner of the engine sitting right in the middle of it.
So, this led researchers to develop a new, far more comprehensive method, a way to finally get an accurate picture of what's really happening at that engine inlet. And let me tell you, this wasn't just some simple fix. It actually required creating a whole new analytical model from the ground up, one that could finally account for both the rotor's downwash and the engine's suction, across all kinds of different flight conditions. What the researchers developed is basically a 10-step recipe for reality. They start with the flight conditions, then they calculate power and how weight changes as fuel burns off. They model the rotor's thrust, and they even factor in what happens when you're flying really close to the ground. And it all leads to one final crucial output, the actual combined air velocity right at the engine's front door.
A new model is great and all, but how do you prove it actually works? Well, you put it to the test against one of the most legendary helicopters ever built.
The test subject for this study was a super detailed computer model of the Sikorsky UH-60A Black Hawk, powered by its real-world T700 GE turboshaft engine. By using a well-documented, real aircraft, they could check their new model's predictions against actual real-world flight data.
So, the objective was crystal clear. Run the simulation through all sorts of flight maneuvers, hovering, climbing, flying forward, and see if the numbers from their new recipe match the numbers recorded from actual Black Hawks doing the exact same things. I mean, this was the moment of truth.
And the results? They were absolutely stunning. This chart says it all. The old models, the ones that didn't fully account for engine suction, were significantly off from the real-world data. But the new model? Its predictions lined up almost perfectly. They had cracked the code. And one of the most compelling proofs of the model's accuracy came from this very specific, kind of weird phenomenon. There's this counterintuitive effect in helicopter flight known as the bucket point. As a helicopter starts moving forward from a hover, the power it needs actually decreases for a second before it starts increasing again. It's this weird little dip. And guess what? The new model predicted this bucket perfectly, proving it really understood the subtle physics at play. Okay, so this is fantastic academic work, but what's the real-world payoff? Why does getting these calculations so precisely right actually matter to any of us? Well, it matters a whole lot. With a truly accurate model of the air going into the engine, engineers can design way more efficient and powerful engines. They can improve fuel economy, which means helicopters can fly longer missions. It leads to safer performance, especially in extreme conditions like super high altitudes or hot weather. Ultimately, this kind of fundamental research leads to more capable and more reliable helicopters for everyone who depends on them.
By finally accounting for that overlooked engine suction, these researchers mapped an invisible battle that's been happening for decades, right above the pilot's head. It just goes to show you that even in our most advanced machines, there are always new mysteries just waiting to be solved. The only question is, what's next?